is Stu, and welcome to Lost in Science. We are continuing this week with our summer series. This week, I am going to take a look back at an interview I conducted last year with Ted Vanderfeen, who's an engineer at CSIRO's Robotic Perception and Autonomy Group. And I also talked to him about his time at NASA through the Australian National Indigenous Space Academy. So please stay tuned.
In the history of science, novel and innovative concepts occasionally arise from sudden left-field inspiration.
Nothing shocks me. I'm a scientist.
But I'd rather be remembered for my own small contributions to science.
As a scientist, I don't want to prejudice my experiment. I'll let you know in the morning.
I am a scientist!
I think they're scientists.
I bring scientists, you bring a rock star.
Across Australia on the Community Radio Network, you are listening to Lost in Science. Just on the topic of robots and robotics, mechatronics, I mean, it sounds like a 90s dance music act. What is mechatronics actually?
Mechatronics is essentially just a mix between mechanical and electrical engineering.
Okay.
So instead of calling it robotics, they thought, well, it's kind of mechanical engineering degree. It's kind of an electrical engineering degree. We'll just chop those words up and slam them together.
We love that. Very German,
yes.
I think.
Yeah. So my education university was sort of half with the electrical engineers and half with the mechanical engineers.
Did that result in you building robots as part of your university studies?
Yeah.
Is that what you did? You just built robots?
Yeah, I had a course in programming robots and that sort of stuff. Yeah.
So you're doing the software programming side of it as well as building actual hardware that can do stuff.
Yep, putting all the electrical components together and actuators and microcontrollers and all that fun stuff. So it's a very systems field of engineering in that you've got to have a broad knowledge of quite a lot of things and how they come together and how they communicate and all that sort of stuff.
And I guess, one of the things that I see people like Boston Dynamics building these machines, which are, they're these multi-purpose, Swiss Army knife robots that can try and do a little bit of everything, and they do it okay. Yep. That's not really what you're focused on. You're focused on building machines that do specific tasks, like you were talking about the space exploration.
Yes,
robots.
Yeah, correct. So I graduated from Western Sydney University and thought, what the heck am I going to do now? I just purely by chance stumbled across the ad for the sort of inaugural cohort for the National Indigenous Space Academy. And I thought, what the hell? I throw my hat in the ring. I'd sort of spent all this time, like the whole reason that I decided to go back to university was because I was so passionate about space and all of the work that NASA was doing for trying to uncover biosignatures on Mars. And it was just amazing sitting at my computer and seeing these photos that had come from another planet within our solar system. So I was like, that would be excellent. Like, it would be such a dream come true to be able to represent humanity in one of the biggest questions in the universe, which is where did life come from? Why are we here?
It's a planet currently completely inhabited by robots.
Exactly. Pretty cool planet, if you ask me.
It is a pretty
mean,
cool planet.
Yeah.
Now, the one that I know you were involved with was looking at, and this is, I remember a quote from years ago where someone said, "We know more about the surface of the moon than we know about the floor of the ocean on Earth."
Yeah.
And I think that's really interesting. But what you were doing is kind of a bit of both. You're looking at submersible robots to explore other planets.
Yep.
Or other moons around other planets. How did that come about as a project?
So that was, again, purely by chance. I sort of, my journey through university, I had the mentality that I'm going to take any opportunity that I can that prepares me for the next opportunity or the next thing that gets me closer to my goal of working in the space industry and that sort of thing. So at university, I did an internship with a company in Western Sydney called Thales with the underwater systems team. So that was looking at designing underwater mechanisms. That was a mechanical engineering internship. So that was mostly, designing mechanisms and stuff that would be deployed under the water for various clients of that company. And I threw my resume into the pool that went off to NASA JPL over in the States. And my mentor, Dr. Andrew Klesch, who's the lead systems engineer for the Ocean Worlds Lab, picked it up and said, "Underwater systems, that looks excellent." He reached out and said, "Do you want to work on underwater robots for other planets?" And I would be very silly to say no.
I mean, it's not often you get asked that question, but when it comes up, you have to say yes, right?
I don't imagine there's any situations under which that would be a no for me. Yeah.
So there are icy or ice-covered moons in our solar system around the gas giants and that sort of thing, and that's been proposed. I mean, this is one of the things that, it's been the question mark for, and talking about life on other planets in general, is life really common or is it really unusual? And that's the big question. But the big thing that we associate with it is water, and obviously a planet that's made of water and has an icy surface potentially has life under the icy surface. So that's what you, I guess, going there. The ice around the surface presents a problem. How do you get through the ice to get your submersible into the liquid?
That is an excellent question. So there were mission concepts that had been undertaken when I was over there. So things like a Europa lander that would land on the surface and deploy a whole team of robots to try and get under the ice. But one of the concepts they had was called the Eels robot, and it was essentially a multiple meter long snake robot. And the idea would be, because there's these, so it's not completely solid, the crust of Europa and Enceladus. There's actually these boreholes. And what they've witnessed these boreholes doing through the Juno probe and other probes that they've sent that have done flybys of these planets is that they're ejecting a lot of material out of their orbit, sort of thing. So they believe these boreholes and this immense pressure that's being inflicted upon these icy moons by their gas giants, like you were mentioning, is just sending all of this water and material out of these boreholes and just ejecting it out into space. And you can actually witness it through things like the James Webb Space Telescope. You can see there's these sort of lines of vapor, like a liquid vapor water, we believe, just being ejected from these planets. And we think that has to come from somewhere. So we've designed robots to potentially sort of worm their way down these boreholes and get under the ice. And so the rover that I was working on was called the Buoyant Rover for Under Ice Exploration. And it's a cylindrical rover, and the wheels are actually designed to fold up. So, and the idea is that you can just send this thing down the borehole, it deploys the wheels, and they become wheels again. And then it uses buoyancy to fix itself to the underside of that icy crust, and then it can drive around and do scientific experiments and exploration and that sort of thing.
It's being held up by its buoyancy, but using the wheels to navigate the underside of the ice.
Yep.
Wow, that's really cool.
Yeah. So a big thing, like the reason we haven't sent legged platforms and other locomotion stuff to other planets at the moment, a big reason for that is power. It's very difficult to get energy to Mars. So the current rovers that are over there are using the previous ones used solar. The current ones are using something called a radioisotope thermal generator, which is essentially a mini self-contained nuclear reactor. And those have about 130 watts, which is less than it takes to boil a cup of water. So they have to be super, super efficient, and the legged platforms and the motors that we have today would essentially knock all of that power out. And if we sent a traditional underwater ROV to one of those icy moon environments, we would have no way to stop it from just floating around and being affected by the currents.
Right.
On Enceladus and Europa, we don't have solar as an option. Because it's under that icy crust, we believe it's completely dark. We've got no idea what's down there. It has to be super power efficient.
And even at that distance, the strength of the sunlight probably wouldn't be great either, I imagine,
Yep.
even on the surface.
Yeah, I can't remember the exact metric, but the Europa Clipper probe they just sent out there had enormous solar arrays because it gets something like 20% of the solar energy that we would get here on Earth. So they've just had to scale the solar arrays up so that it can actually get enough energy to operate.
And probably sit around for longer waiting to power up as well.
Yeah.
Congratulations on your discovery, which may well prove to be among the most significant in the history of science.
I cannot accept half-baked theories that sell newspapers. I'm a scientist.
Who are you, who are so wise in the ways of science?
A most distinguished scientist, whose name we know, even in the wild of Transylvania.
Across Australia on the Community Radio Network, you are listening to Lost in Science.
You are listening to Lost in Science, and I'm talking to Ted Vanderfeen about his work on extraterrestrial exploration, and I'm just going to continue my discussion with Ted. I'm asking him about the National Indigenous Space Academy with which he was involved recently. Now, another thing that you mentioned is the National Indigenous Space Academy. Can you tell me a little bit about that and how you came to be involved with that?
Yeah, so that is a program that's run by Monash University, and every year, and the program has just expanded since I've gone, but every year they send 5 or so Indigenous university students, undergraduate or postgraduate, over for a 10-week internship at the NASA Jet Propulsion Laboratory. And they've just expanded that to another space research lab in the UK this year as well.
Oh, so they're sending students over to the UK as well.
Yep.
As JPL.
So this year, I believe they're sending 6 students to JPL for 10 weeks and 2 students over to the UK at the same time. And when I first started, it was a program that was supported by the Australian Space Agency.
Mm-hmm.
And about a year after we got back, they reaffirmed that funding for another couple of years. And CSIRO's come on board to fund it as well.
So, I mean, people don't think of Australia as far as being a spacefaring nation all that much. Do you know much about how the National Indigenous Space Academy got started, and what was the thinking behind it?
Yeah, so it's the brainchild of one man. So Dr. Christopher Lawrence, he's always had this idea and he's always wanted to send students. He's got this grand dream of enabling the first Indigenous astronaut to be the first Indigenous astronaut. So he really is super passionate about providing these opportunities in the space industry for Indigenous students. And Monash were just crazy enough to say, okay, we'll support you to do that. So he set the program up, and yeah, it's in its third year this year, and I don't see it losing steam anytime soon.
No, and I, one of the reasons I wanted to get the word out there is, you can only have a successful program if there's enough applicants, but I'm sure there are enough people who want to get involved. I mean, who wouldn't want to go for a 10-week internship at the Jet Propulsion Lab? That would be enormous fun, over my head.
Honestly, a life-changing experience. I would not be where I am today without it.
So what activities, or what did you actually do while you were there during the internship?
Yep. So I was working on the Brewery rover to essentially give it obstacle avoidance capabilities using sonar. So sonar is an underwater sensing solution that uses sound waves to roughly guess the range of the thing that returned that sound wave. So my task when I was over there was to adapt off-the-shelf sonar module onto the Brewery vehicle and then give it the sort of software machine capabilities to be able to say, okay, there's an obstacle there. I'm going to alter the path that I was going to take to now go around that obstacle that I've detected.
And that's what you were working on while you were there. So an actual project,
actual robot. Yep.
Has potential to go into space and do stuff.
Yep. So I was working on the Brewery rover when I was over there, and I actually put a grant application in after I left based on the work that I did to continue my work, which has been pretty cool. And I've been catching up with my mentor every now and again. You said, sort of just giving me updates on where the project is, and it's sort of like it wasn't work that I just did that was busy work.
Yeah.
I was really made to feel like a part of the team as soon as I got there.
You weren't doing the photocopying.
No, I wasn't fetching the copies. I was actually getting to work on the robot, and I got to hand that work off, and it's been continued now, and it's a funded NASA project that's been funded through the ROSA scheme, and a whole team of people working on it now. So
yeah, that's a great endorsement of the project altogether, really, that you're actually doing real work and it's ongoing. And that's that is how science works. There's not something where you can go, here's a 10-week project and it's done. That is not ever something that happens.
You always end up finding more interesting questions along the way, I found.
Oh, that's almost the point, is not not your results, but the questions that you didn't answer that you get to. One last question I have, and I've seen this in a couple of places, that you are working with space-based neuromorphic vision sensors.
Yes.
What on earth does that mean?
So that was my honors research that I did, and I was a research assistant in this field for a little bit. But essentially, a neuromorphic vision sensor they're known by a few names. So event cameras, silicon retinas, and they aim to be like a hardware implementation of how the human eye functions. So with a normal RGB red, green, blue camera, you've got 3 color bands, and it captures a whole frame of like pixels at once, and that's an image.
Yep.
But with an event-based or neuromorphic camera, every single pixel kind of operates as its own little camera, and it's responding to changes in luminosity from the thing that it's viewing. So it's like whether the brightness goes up or it goes down. And essentially what that gives you is you get instead of getting a whole frame of pixels and a lot of data, and it's very power hungry, and you've got these fixed time slices of photos, an event-based camera will update as things move across the frame. So you end up getting a continuous stream. They're like the same speed as like a high-speed slow motion camera. It's like nanosecond, microsecond latency. And you essentially just get a really clean picture of the things that move through the frame because they excite the pixels as they move around the sort of field of view of the camera.
So it's basically recording changes to the image that it's already got.
Yeah, it doesn't. If nothing changes, it doesn't update. Yeah.
Yeah, and that saves power because you're trying to reduce the amount. So that's a really amazing bit of technology.
Yeah. So that was the partnership that work was through was with Western Sydney University and NASA. They'd mounted one to the Columbus module on the International Space Station. They'd actually mounted two. So they mounted one that was looking at the horizon and one that was looking straight down, and they were attempting to catch something called sprites, which is essentially high altitude space lightning. So when and it's super poorly understood because they're so transient, like they're over within like nanoseconds.
Yeah.
I mean, it happens over the top of lightning storms.
Mm-hmm.
And it's instead of the lightning sort of grounding itself to Earth and going down, it goes upwards towards space. And they're bright. You should Google it because they look so awesome. But the idea was that we can put these super high-speed cameras that only capture changes on the ISS, and we might be able to capture some of these sprite events.
Yeah, right.
Yeah.
Did they capture anything?
I believe the section of the project that I was working on was early stage, and they were saying, okay, will these cameras even work in space? Like, it was the first time anyone had sent these cameras to space and had them work. What do we need to know if we're going to deploy them again? And they actually did end up deploying them again. So the mission that I was involved with was called Falcon Neuro.
Yeah.
And the follow-up mission that was sent after my time at the lab is called Falcon Odin. And that's using newer, more impressive neuromorphic sensors and all of the lessons they learned from sort of the first stage.
You've done all this stuff. What are you up to at the moment?
Yes, so I got back from the States and NASA, and I thought, wow, that was really awesome. I want to do robotics research. So I ended up joining CSIRO. I'm working with them and doing my PhD at the QUT Center for Robotics at the same time. And I'm looking at a similar vein to what I was doing at NASA, extreme environment robotics. When we send robots into environments that humans can't or don't want to go, so disaster sites or planetary surfaces, an example I like to use is like, when your robot vacuum at home runs over a sock and you have to go and pull the sock over its mouth and flip it back over. We unfortunately can't do that with robots exploring other planets.
Yeah.
So how can we make them more resilient, more robust to stuff that happens? How can they respond and fix their own problems so they don't have to stop and ask us for help?
Yeah, right. That's what I was going to say. So you're working on ways that they can solve problems which are not necessarily predictable problems, but sort of give them, I guess, general problem-solving abilities.
Yeah, give them the tools to introspect on what's happening in their own internal systems and say, oh, I got an error, but that error is fine. I don't need to worry about that. I'll continue. I won't stop. I won't hold up science and send a message back to Earth, which takes 7.5 minutes. I'll just continue on because I know that error is inconsequential.
Right. And how are you actually going about doing that?
A lot of simulated experiments. So a lot of data collection and deploying stuff on actual robots. Making them fail on purpose, which feels bad sometimes. So if you've seen some of the Boston Dynamics videos, they'll show how robust those robots are by hitting them with the hockey stick.
Yeah.
And saying, these guys aren't going to fall over, so they'll just keep whacking it. I don't hit robots with a hockey stick, but it's a lot of things like inducing really poor perceptual conditions. So like shining a light, saturating the camera's dynamic range so it can't see anything. What does that affect? What effect does that have on things like how does it localize within its environment and how does it navigate and make decisions? So inducing sort of the edge cases. So when you deploy robots in the real world, there's going to be stuff that you come across that you couldn't possibly have predicted. And with that, all of the design choices you made potentially aren't going to hold. So you've set a lot of thresholds and stuff and all these values within your robotic system. And if something comes along in the real world, which it often does, like you can't predict everything that's going to happen in the real world, that violates those assumptions. How do you overcome that and deal with it so that you're more resilient when you need to be in these super critical things where we can't just go up to Mars and reboot our rover. Have you tried turning it off and on again?
and the cost of each mission is so high that you probably don't get a second chance if it doesn't work the first time either.
Yes. Yeah.
So it sounds like you're kind of making conditions for them as bad as they can be without them breaking.
Yes.
And seeing how they respond.
Seeing how they respond, seeing if we can use that sort of data signature of how it's responded when it's gone bad so that it knows something has happened next time. because robots don't necessarily know when something has gone wrong if
No.
we haven't explicitly told them, hey, this is what it looks like when it goes wrong.
So you can look at their reactions to these events and tell it next time that happens, don't worry about it.
Yes.
Just sit still for a second and then carry on when that thing stops.
Or
affecting
trigger
you.
trigger a recovery action or
Yeah.
But if we can say this is the evidence you need to look for in order to say that you've misdetected something or you've taken a wrong turn somewhere.
Yeah.
When that happens, trigger some action.
So you're basically building them to protect themselves, which is probably a nice thing to do for the robots.
Giving robots feelings, someone told me the other day.
Let's not go that far. Then if we give them feelings, we definitely don't want to be hitting them with hockey sticks, right?
Oh, absolutely. Yeah. I think that all the memes about the robot revolution might come back with force then.
Yeah. All right. Well, I really do think we'll have to wrap it up there, which is a real shame. But I'd love to catch up with you another time. But thanks for joining us on the show, Ted.
No worries. Thanks for having me, Stuart.
And good luck with your PhD.
Yes. Thank you so much.
And that is all we have time for this week on Lost in Science. Thank you for joining us in Getting Lost. If you have any questions or suggestions for the team, get in touch with us by email. We are lostinsci@gmail.com. You can send cheap tweets to us at lostinscience1 on Twitter, or you can find us on the ubiquitous Facebook. Lost in Science is recorded at the studios of 3CR in Melbourne on the land of the Kulin Nation and is broadcast across Australia on the Community Radio Network with the assistance of the Community Broadcasting Foundation. You can find a podcast version of the show on 3cr.org.au, or you can tune in the way you did this week when we return in our usual time slot to get Lost in Science!